Hey, welcome class. Today we're going to learn about the Spark. Spark is an open source in-memory distributed cluster computing framework. Currently, Spark has replaced many open source and vendor-based big data tools, especially the Hadoop MapReduce batch job. So Spark can be run in different modes, and they can be categorized as with or without Hadoop. Without Hadoop, Spark can be run in a local system in a local mode, meaning that you can just run on your laptop or a PC computer or even Mac or Linux for that matter. So that's a local mode, and you would use that for either for learning during learning process or even for the development process. But for the quality and production systems, Spark is run in a cluster mode. So in real time, we would see that a typical production setup would be that a Spark is running on top of a Hadoop cluster with a Yarn as a resource manager and HDFS as a file system, distributed file system. So in either case, to access the Spark cluster from a driver program, we would need something called a Spark context. Spark context is the entry point to the Spark cluster, either running on the local mode or on top of a cluster like a Hadoop cluster, right? So how do we create the Spark context? It can be done in two modes. One is the interactive mode and other is in application mode. In the interactive mode, we would use a command called PySpark, and then we would indicate the master. If you're running as local, you would simply indicate local and also the number of processors you want to use in the local mode. If it is Yarn is your resource manager, then you would mention the Yarn here. So once this command is successfully executed, Spark will create a Spark context for you automatically with a variable name called SC. But if you're writing an application, that is you're running Spark in application mode, you would need a command called Spark submit. Along with the Spark submit command, you would also mention the application file name. Within that application file, you need to create. So it will not automatically be created for you. So obviously you got to manually create the Spark context. And then after you create a Spark context, you can go along with the rest of the program, what you want to do with that particular application. We'll see that in a later session. But at the minimum, you need to first create the Spark context. So in order to do that, you would use a API Spark conf and Spark context from the library called PySpark. So from PySpark, import Spark conf and Spark context. So this is the Python equivalent or PySpark code. So then with the Spark conf, you would mention the master set in the set master and also the application name, and then you create the conf variable, that is a configuration variable. You would also, if you want to know more parameters associated with the Spark conf, you would simply say help and within the parentheses mention Spark conf, and you would get all the options that's available within the Spark conf. But at the minimum, you need to mention the master and application name, and then you would use the conf variable to create the Spark context. And likewise, you would also, if you need to know what are the more options that are available for the Spark context API, simply type help and within the parentheses mention the Spark context, and you would know what are the additional options that are available. But at the minimum, this is sufficient for you to create the Spark context. And then now question arises, what are we going to do once we have the Spark context? Okay, I have Spark context, now I have access to Spark cluster. So once we have access to Spark cluster, we need to do three tasks basically. One is that we read data either from a raw file system or data lying on the HDFS, or it could be from some database, or it could be from any other source of data. So we would read data from the source and then we perform some operations on it, and then finally we will output in the required format. So these are three operations we do. So to perform all these Spark operations, fundamentally we do all this with an abstraction called as RDD. RDD is the fundamental abstraction in the core Spark API. RDD stands for Resilient Distributed Dataset. So this will crack down what does each of this word imply. Resilient. So why is it called resilient? It's called resilient because it maintains something called a lineage of all the operations in case of failure to recreate the data object back. That's big, right from the reading onwards, right from reading the data into the Spark cluster and followed by all the operations. It keeps track of all those operations. So in case at any point where if this data is lost in any one node or a couple of nodes, it has capacity to recreate the data back. And that's the reason it's called resilient. And it's distributed, obviously, because when it's run on a cluster mode, the data is distributed across the executor nodes based on the task. So that there's a default behavior and where the Spark itself is smart enough to figure out how to divide the data or the task into the and assign to different nodes. But there's also advanced options where you can tune and exclusively mention how many partitions you want and what partition nodes you want to perform tasks. You would also have that level of control. Those are advanced options, but even the default Spark behavior itself will give far better performance, especially compared to the Hadoop MapReduce. And the third interesting feature of RDD or with the Spark itself is that it evaluates each operation or each code with something called as a lazy evaluation. That means that, let's say, if you're familiar with Python or even any previous or any other programming languages, you would see that each line that you execute, your compiler or interpreter actually going to execute that particular line of code and allocate or deallocate the memory based on that particular line of code, right? But that won't happen with the Spark. So Spark knows that it's not going to perform for every line of code. What it does is that until you would need a final output, it will not evaluate all the previous transformations. So we'll see what is transformations and actions imply. But basically, until you would need something, an output or action, it's not going to perform anything, but it keeps track of all those operations. And once you need it, then it pulls the data and bring it to memory and performs the operations and throw back the result, right? So at the very basic, there are different types of RDDs, but we would focus on four main categories. One is the basic RDD, numeric RDD, paired RDD, and schema RDD. In real world, you would use paired RDD and schema RDD, which is also called as data frames. 80% of time you would use these two type of RDDs. So first we'll start with basic RDDs. We'll see some activities on the data. So let's jump on to that. So generally the RDD operations are divided into two categories. One is called as action and other is called as transformation. So if the data is being interacted between a driver and RDD, then it's called action. For instance, you're reading data from some driver application, that is a local file system or database, into an RDD, that's action. Or conversely, you actually going to send the output of the RDD and save it on a driver file system. So either of these are called actions. And not only file, even the command line interface. If you're doing interactive mode, you want to print the data, so then the RDD is transformed into the console to show up on the screen. So even that is considered as action. Whereas transformation, an RDD is transformed into other RDD with certain function applied and via APIs like map, filter and flat map. We'll see more of these APIs. So in transformation, basically an RDD becomes another RDD, whereas here an RDD would typically an RDD would become from a file, or RDD becomes a file, or RDD prints or outputs and into the command line interface. Okay, so those are the actions, and this is the transformation. So some of the familiar APIs or most used APIs for transformations are map, flat map, filter, distinct, group by. So you would also see that there's a option here to preserve the partition. So you can actually mention the partitions if you know what you're doing with it. But otherwise you would leave these options. But basically the map, we would use the functions. We'll see an example of it. And then flat map, filter is basically a row level operation, and distinct of course going to take out the duplicate rows. And this is group by, where it creates an iteratable objects. We'll also see what it is. And then we also have other operations, the set operations, the set transformations, union. Of course, when we say set, we're talking about between two different RDDs. So we have union, we have intersection, that actually, so let's say we have two RDDs, one is even, another is prime, and if its intersection is going to bring the common data, union is simply going to combine all the data, subtract the first minus the second RDD, and whatever data that is left, that is a subtract, and partition is the all possible combinations. And of course this is not recommended in the production. And coming to the actions, we have RDD count, that indicates how many rows it has. RDD first, it will print the first row, and you have take, and you can indicate the number of rows, number of objects you want to print onto the console. And collect would actually bring all the data, and again not recommended in the production. And you also have for each, and then function name. This is a little confusing because it looks like on the surface it looks like it performs same thing as a map, but it's quite different, right? We'll see each of these examples as in the lab section. And then we also have reduce and fold. So these are important actions as well. So reduce and fold are same, except that fold would accept certain initial value. This is helpful because at certain times when RDD is empty and you're performing a function on it, it's going to throw an error. Whereas if using fold, you would actually get an initial value even with an empty RDDs. And likewise, you also have aggregate. Aggregate works with initial. You need to provide initial value, sequence operation, and combiner operation. And the important point to consider here is that unlike reduce and fold, aggregate can return RDDs with different data types. Right? An example would be that aggregate provide. So let's say this is the RDD even with the 0 to 4, and then you want to know this. It's in a single command, in a single line of code. You want to know the summation of all the elements and also the count of elements. So you would start with 0, 0. The first 0 indicates for the initial value for the sum of all elements, and second 0 for the initial value for the count of elements. So sequence operation here, x of 0. So x would be the 0, the initial value, x of 0 plus the y, the actual value of the actual element value of the RDD, and here we would simply, since it's a count, we would simply add a 1. And during combining operation, we would simply combine each of those elements, and then the result we get is 6, 3, because summation of all the elements is 6 and count of elements is 3. So with this we'll end the session here. So once we do the hands-on, probably things will get clarified. Thank you all.